manufacturability using SolidWorks plastics. I'm Joelle Guinette, and I'm the territory manager for SolidWorks for Eastern Canada. And I have with me Michel Cloutier, who's the technical manager for the area. So we cover Ontario to the Maritimes, and if there's anyone joining us from the Eastern U.S., we welcome you as well on this call, as we're going to go through some very interesting information this morning. Before I go through the information, I do want to let you know that on your panel on the right-hand side for GoToMeeting, there is a type message here area where if you have questions, please don't hesitate and enter them there so that we may address them at the end if possible, or take offline and follow up with you afterwards. Just above that, there's also a handout that you can download, so you can see some additional information on plastics solutions from SolidWorks from this data sheet that you can download for yourself if you want at this time. So let's jump into our topic this morning. Why are we talking about this? Let's take a look at traditional or historical way of developing plastic parts. The process that's normally followed follows these lines. Part design is first done, then mold design. Once the designs are done, we go to mold manufacturing. Then, of course, the parts can be produced. And then we go to product launch and go to market with it. So in the beginning portion of this procedure, of this process, influences immensely the manufacturability and the quality of our parts. So how the parts are designed and how the molds are designed both have an impact on these aspects of manufacturability and of quality. So if they're not obviously verified, if they're just simply designed, then this can be, you have less manufacturability and less quality. Then you move on to the next section of the process where you're making the molds, you're making the parts, then you increase the responsibility that you have as a manufacturer to meet your requirements that are expected either from the person you're supplying this to or the consumer that's going to be buying these parts. This is where your guarantees need to hold up, and we want to have your part have the best quality. So let's take a look at some options of how this is typically done in the design of plastic parts. So the part is designed, the mold is designed, the mold is built, we go to production, and something is detected that the part has a defect at this point. Then what do is we circle back. So they can go to in-depth simulation at this point, which may be one solution. It may be done in-house. It may be done by somebody else who has more expertise in the simulation. Or simply the process can circle right back to part design, mold design, with iterations of trial and error, of let's see if we can try something else that will make it a little better. This is obviously very costly, very inefficient, and when all is said and done, hopefully the problems are fixed, but there are obviously better ways. So we're not quite there yet, though. We have another alternative, which improves things a little bit, where at least simulation is inserted at the mold design section, so that you make sure that your molds that you're designing for plastic parts are going to be properly done, and you've got confidence in that section of things. So that's one way of doing it. Now let's, actually there's a little text, sorry. This is obviously a limited application. It provides some benefits, but you could still have some issues at the end of the day. As we're doing this, obviously people who are doing this are basing their designs off of a lot of experience. And there's great value in that experience. But sometimes, even as a designer, you're asked to do something that's new, that's different, that may be smaller, that may be just a little more challenging. And at this point, experience takes you to a certain degree, but it would be a whole lot better if you had the confidence of simulation behind it. And the optimized way, or the preferred way, would be to be able to design your part, simulate the part so that the part itself is manufacturable, will give you the quality that you want, design your mold for it, and have that also simulated, either whether you're doing it or another company is doing it, making sure that that section is simulated as well before you go to manufacturing anything at all, so that your end result is as optimal as possible. has the best quality, and you're sure that it is manufacturable at that point and that you're not coming back to do it. Because as you're doing all of this, there's a cost to doing the work up front, which is the case here, versus doing it at the back end. And in our next slide, we illustrate how this cost is propagated. So you're going to say, well, if I do all of this work at the beginning, I have to, one, invest into simulation tools, which is going to cost us some money. We're going to have to learn how to do this, and then we have to take the time to do the simulation. And the reality is, yes, you have to do all of that to be able to do the simulation at the beginning. But the reality is also that this will cost you less, will have a less impact on the overall cost versus having to take a design that's already been done, a mold that's already been manufactured, parts that have been manufactured, and come back and start back at the beginning. So this illustrates this in a bit. Best to take the time up front and spend and invest up front in doing this versus the cost at the back end. So with this optics, we have information today on the first part of this, which affects your part design. So Michelle is going to take you through some information on how to optimize plastic parts and how to get them right the first time so that iterations don't have to be done. And we have a section next week that's scheduled to go into the later part of the design, which is how to simulate your mold manufacturing, so that that portion also guarantees you the best success in your part production. So I'm going to transfer this over to Michel. Michel has been with SolidWorks. For those of you who don't know him, he's been with SolidWorks for 14 years. He has seen the evolution of our simulation portfolio into plastics and to more applications and greater tools even just within the plastics portfolio. So it's very exciting, and he's going to take you through this information. I'll come back at the end to close this off. Off to you, Michel.
Awesome. Well, thank you, and welcome everyone to our session. Like Joelle introduced us to the topic, what we want to do today is see how we can, optimize and simulate our molded parts and molded designs as early as possible. This is a little overview of what I'm going to talk about today, but just to break it apart, I'm actually going to start within core SolidWorks because there are quite some tools inside of SolidWorks, not only to help you design, but also help you do some analysis inside of SolidWorks before you ever get into plastic simulation. Once we do that, then we are going to move to plastic simulation, show you how to actually set up a simulation, how to run it, how to look at the results and interpret the results and understand them. And then we're going to go through actually a number of scenarios, just to make sure that we find the best design possible. And then we're going to touch a little bit on actually mold design, which includes family molds and runner balancing. So we're going to brush off on that at the end. So let's start with the beginning. Inside of SolidWorks, before we go to plastics, we're actually going to explore a few of the design tools. And I like to explore those with you because those are really design tools geared for molded plastic parts, things we see quite often into a plastic part. If you have a old TV remote and you take it apart, you're gonna see some of those features in there, that's for sure. So I gotta cover some of those and see how we can use them inside of SolidWorks. So let's just jump in SolidWorks and see how we would use them. So as I'm moving inside of SolidWorks, this is going to be the example I'm going to be running with today, a little smoke alarm. And if we isolate this area, we see a PCB board, and we need some mounting bosses to support that board. So I'm going to simply, in the assembly, edit this part. And as I'm doing that, I want to just show transparency so we can see a little bit better through the PCB board. And as we can see over here, there's already a mounting boss set in there to support that PCB board. We want to create another one for this hole here. Now, how do we go about doing that inside of SolidWorks? As I said, very easily, I do have my, my features here, and one of them is a mounting boss. The only thing I need to select here is a face where to set this boss. I already have a great preview. We have different options for bosses, so either a hardware boss with a head or with a thread type design, or it could be a pin with, again, a pin design or a hole design. So all the variations are there. It's really about you selecting which one works best. And then when you do that with a great preview you get on the screen, you can go in and define all of the dimensional information for that feature. So you don't have to draw anything, you just have to select the right size that works for your design. Now, additionally, if you want to standardize, what I like to do quite often is actually create favorites. So this is my favorite hardware mounting boss dimension. I select it, everything is preset. The only thing I need to do at this point is to select where it's going to be located. So I'm going to pick the circle here of my PCB board hole. I select it. Last thing I want to do is orient the fins, and you can see the fins are kind of or not oriented the same way. So I'm going to pick an edge to help them orient the same way as the other one. And very quickly, I've got this done. That's how easy it is. I got the whole feature. I didn't even have to sketch anything. Everything is ready to go and ready to get to the next step. And the next step, I'm actually going to show something different. Let me just rotate the model around and zoom into the battery area. So in that area, what I want to do is to design a hook that's going to snap the battery in place. We already see some hooks designed over here. That's for the core cavity, but I want to design and show you how we can create those very easily again inside of SOLIDWORKS. So again, one of the tools I got, the fastening tools I got, is a snap hook. How does it work? Again, very easily. I select where I want it to be located, the direction, I use a face as a direction. I want it to be flush to the side face of the battery, so I'm going to select the face here and say reverse direction. As I did with the mounting boss before, I could come in and tweak all the dimensions or use a favorite. And as for the height, I want to again repurpose the actual part here and say it's going to be flush to the top face of the battery. And with a great preview, I know exactly what I'm going to get. I click OK, and I'm done. So again, that hook feature, the snap hook feature, really useful when you want to create those designs really, really quickly. Now, the other thing I want to do here is let's go over here to my orientation, and I'm going to get into that section view. And if we zoom in, so let me just go and modify the section view and push it in a little bit further. And as you'll see quite quickly is that over here, I've got my snap hook design, but in the other part next to it, I need to have that groove that's going to accommodate the hook, right? So let's go ahead and see how we would do that. Again, in the context of the assembly, I'm going to edit the top part. And I got the feature snap hook groove designed specifically for that. The only thing I need to define is what is my hook. That's my snap hook. In which part do I want to design the groove so that it's going to be into this one here. I select it. And then I just have to specify the dimensions of the groove, click OK. And again, SOLIDWORKS goes ahead and creates that for me without having to sketch anything, design anything. Everything's done, everything's easy. There we go. So as you can see, there's quite some nice design tools inside of SOLIDWORKS just to save you a lot of time just on the design side of things. Next, I want to talk about, again, inside of SOLIDWORKS, some of the analysis tools we can use inside of core SOLIDWORKS to help with plastic design part, draft analysis, undercut analysis, and things as such. So again, let's switch back to SOLIDWORKS. And in this case, I'm going to go to this part. This is my, my cover for the alarm system, or the the smoke alarm. And inside of SolidWorks, inside of my mold tools, let's explore the first one that probably everyone uses in a very common way, is the draft analysis. One of the key things when you have a molded part is to make sure that you have a good draft analysis on those faces. So I'm going to set my draft analysis to 1 degree, and now we have a nice color code all the way around this part that shows us the draft and the properties of those draft. So if there's any faces that need draft, we could fix them quite quickly. Actually, I wanted to show you actually this part. So let's switch components and instead go over here and open this part. So I actually wanted to show you one of the designs that had a draft problem, so we can show you how we can fix it quick. So over here, again, let's launch the draft analysis. Very easily select a face for the pull direction, select an angle. There we go. So this is actually what I was kind of looking for. I was actually looking for an issue so we can fix it together. And we see here that we have positive draft in green, negative draft in red. That's all good. But in yellow, those are the issues area. So there's no draft here in yellow. One of the nice things I like about SolidWorks as well, when I do the draft analysis, as I move my cursor on those faces, I have a real-time readout of the actual draft angle on that face. So as I move around, I can tell exactly what's the draft angle at that particular location. When I click OK, you're going to notice that the draft angle actually stays active. And it does that so it helps me figure out when I add my draft, and I'm going to add a draft to those yellow faces. So it helps me figure out if I'm doing things correctly. So I selected a face for my draft angle. I'm selecting the faces to add draft to. And after I do that, you'll see that the model simply updates becomes all green, meaning that all my draft issues are away now, or gone away. So I got a good draft analysis. I got good drafts on all of the faces. One of the other tools I like to figure out with SolidWorks is the undercut analysis. Similar to the draft analysis, the undercut analysis is going to show you faces where there's an undercut, which in the mold world would mean that you probably would have to have some side actions into your mold. So that's a really quick way to understand if your cost of the mold is going to go up because there's more complexity into your mold. So very quickly, I'm able to figure out that these areas here you see in red. So for that, I'm going to have some special operations into my mold to figure out how to pull this or open the mold. So I'm gonna need some special operations again in my mold, some side cores and things like that. So with some of those tools, you can also use them to help you eliminate some design flaws that could creep up into your mold design or part design very quickly to eliminate some of the errors downstream. Now, next thing is that we actually want to start doing a plastic simulation. So here I'm going to show you how to actually create from scratch in a part, how to create that plastic injection simulation by selecting the material, running the analysis, and later on, we're going to look at some of the output results. So again, and I'm going to do that live, mind you. So everything here is going to be done live. So let's go to our mold here, not our mold, but our part. And I'm going to start. Actually, I'm going to leverage quite a bit the configurations inside of SolidWorks to do that. So as I do that, so let's quickly reorient it. and actually over here, that's the orientation I'm looking for. And as plastics is an add-in to SolidWorks, though in the add-ins, you see it's already turned on. So I'm gonna create a new plastic simulation. So the first step is going to create a mesh, which is familiar. If you've done FEA before, it's very familiar. If you're not, it's still very easy. We could do it automatically without much input. I'm actually going to create this one manually because I want to give it, because I'm going to be running this live. I'm going to start with a fairly coarse mesh size so it runs good and we don't wait too long for results to come back. But very quickly, I'm able to take this model, create a mesh, and once my mesh is created, I click OK, and I'm basically ready to go to the next step. I need to define two more things before we actually run the simulation. First thing is the material. So I can go over here in my materials, open up the database. Now this database has hundreds, if not thousands, of materials already set in. So based on the plastic type, so I'm going to actually use a PC material. Based on manufacturers, there's quite a bit in there that's just PC, so a few hundred. So there's like thousands of materials in here. So for now, we're going to use a generic PC type material, and we can see the viscosity and all of that information about that material. And you can also create your own user materials as well. I'm going to use the one in the library, which is fairly a generic one. I've set the material. The last thing I need to do actually in this before I run the simulation is to set where's my gate. Now I think that a gate location somewhere over here might be a good area. So I'm going to select it on the screen on my model. It's going to be a 3mm gate size. I say I want to add location. Click OK. So very visually, I know exactly where that gate is. And at this time, at this stage, I just need to run the simulation. Now I'm actually, again, running this live, with you guys. And as it's running, we can see some results in the window here. So we can actually see the pressure at that stage, at that percentage of filling. And we can actually see the mold that's starting to fill on the screen. So as it's doing its calculation, it's also starting to show me some preliminary outputs and results. So if I see something, totally off, I could actually just kill it and maybe decide on a different ejection or gate location. But very quickly, I'm able to get some outputs. So as this is running, I'm actually going to minimize this and go back over here. We'll look at the results just right after that. But I hope you can see how quickly it is to set up a simulation, a plastic simulation, and how easy it is. Very quickly, I've created three things, really: the mesh, define the material. Once the material is defined, you just need a gate location. And for something simple as this, that's pretty much all you need for it to run. Now, as the simulation is actually finishing up, we're going to look at the results and see how we can understand those results to figure out if this is a good part or not. And then we're going to do some reporting to share those results with other team members, for example, and see how we go about that to see if our part can be molded correctly and is a good part. So when your simulation completes inside of SolidWorks Plastics, we get this output, which is the fill time. The first thing I like to show or kind of draw attention to is that result advisor that gives you, kind of a green, yellow, red light system that's telling you if it's easy or not to fill this part. It's actually telling me that the maximum injection pressure is 33 megapascal. Most injection press machine will probably run around 100 megapascal. So I'm actually using not quite as good the capacity of my machine. I'm just It could actually be take a lot more. That's basically what it means. But going back to my part, we can look at different outputs. So the first one is going to be the fill time, and we can run a animation of that as well. Now, what is kind of neat here is even, if you're a plastic part or plastic designer, you can probably pick up on a couple of things here. There's that effect, what we call race tracking, where the mold front on the wall is actually coming faster around the part than it's not filling uniformly. So that's a phenomenon called race tracking. Usually that means that my wall, or it means that my wall thickness is too thick. So we want to eliminate that. But we can also look at other types of outputs. So one of them in there is going to be the cooling time. And we look and we see that the cooling time is actually quite high, 46 seconds. So that means that this part has a long cycle, manufacturing cycle. And the cooling time, if we want to get that lower to be able to produce more parts in the same amount of time, is one of the solution is going to be to get the wall thickness down. So very quickly, we're able to see in this part that already there's, the wall thickness is too thick. We kind of deducted that because of the race tracking effect. The cooling time is quite high. If we can look at some of the other outputs, we can look at the weld lines. Then looking at the weld lines, we see that there's actually a lot of weld lines located in the grill area or the opened out areas. Now we want to avoid weld lines as much as possible, although we can't. In a part like this that has internal openings, there are going to have weld lines, but we can strategically decide where, or depending on the gate location, where those weld lines would be. And this is going to have a negative effect on the structure of the part. It's going to be weaker in the weld line. So we want to avoid having weld lines in an area of the part that's already weak, like those openings. So that's something to keep in mind a little later on. We're going to see how we can fix that. But we can also look at air traps. Again, another common problem in mold making is get rid of the air inside the mold so it doesn't burn the part. And now we can quickly see where the air traps are located. If they're on the split line, usually that's good because the air can vent through that split line. But it can also be a really good indicator to where to position ejector pins, again, as a method of venting the part. And the other thing that the other outputs, there's just so much outputs, I won't go through all of them, but what's kind of neat here is that we can also create a summary and a report quite automatically from this. So I already created the report yesterday, and I'm going to show you the output. It actually creates three types of output, or it can create three types of reports. The first one is a Microsoft Word report. And again, this was done automatically. I didn't edit any of this. It was just a simple output with all the information about my part, the material I'm using, with a graph for the viscosity, all that information. Again, my fill settings, my flow summary. And then down here, all the outputs selected for my report. So I got my fill time, pressure at end of fill, temperatures. So all of those reports or outputs can be captured in a Word document. And that's basically one push of a button, quite literally. You just say, what do you want to capture? And it goes ahead and captures all of this. Even has some of the problems we identified earlier. For example, over here, the weld lines, the air traps shown here. So all of that information captured in a Word document. We could also output a PowerPoint or even a HTML output. Now, the nice thing about the HTML, you'll find pretty much the same information, but in the HTML, you can even have animated images in the HTML output that shows all of those simulations, those outputs. So a great way to share all that information and create that information, but really it's to understand what's going on. So quickly, when we look at the outputs, we understand if there's any issues with the part, with the design of this part, and we can start doing assumptions as to how to fix them. And that's exactly what we're going to do next. We're going to go ahead and explore multiple scenarios. Now, what could those scenarios be? It could be scenarios about a model change to design a better part, maybe change the gate location, maybe change the materials. And that's actually, I'm going to be doing a mix of all of those actually. So the first issue that we saw on this part, it was, the wall thicknesses were too thick. So that gets the cooling time way up, too much time to cool down, can introduce other errors like sink marks, which we could show on a graph, by the way. I didn't show those, that output, but that's one of the outputs. So let's start by doing a model change and see if we can make the part thinner to reduce the cooling time, have a better injection profile, and things like that. So let's get back into SOLIDWORKS. For the other outputs, I actually already ran the simulation to save some time, but I'm going to, like I said earlier, leverage configuration. So I got a configurations here that's thinner. So I'm going to jump to the thin configuration. So you see the sidewalls are fairly thinner compared to the other one. And that's going to actually highlight another issue that we see quite a bit inside of injection molding. If I show the results, you'll notice something. Some of that part is actually grayed out. That means that this part is not even filling completely. In the lingo, it's called a short shot. So even though the first part would have worked, it was not ideal. It was not. It was too much plastic, too long to fill, etc. This one is actually a defect. It doesn't even fill completely. This would get out the mold. You would throw it away. That's how that's a really bad thing in mold making. You don't want to get a short shot. So you can actually understand those short shot and see if those are going to happen. I'm going to change to another model that's the thickness is kind of in between the first and second, and see if that works well in my design. So that's my configuration here. Let's read the results. So now we're showing the results. We're showing that it's actually filling completely. So that's a good thing, right? It's the fill time is going on fully. Now the other thing, another issue that we've illustrated earlier was the weld lines. Now it's still filling. It's the good happy medium for thickness, but I still have a lot of weld lines. And as I said earlier, weld lines are, you can't completely remove weld lines, but you're going to try to avoid them as much as possible, or strategically have them located in a part that doesn't affect the structural integrity of the part, because weld lines is a weak point in the part. So, and we see that we have a lot of weld lines already in a weak area of my part, which is those openings. So how do we fix that? Well, one method we could use and see how it affects the weld line is to change the gate location. So I got a configuration here, and I've moved the gate location that was originally on the top, and I moved that gate location to be on the side in an effort to hopefully get rid of as much as weld lines as possible. So you see now my new gate location is right over here. Prior, it used to be here. So I'm hoping that by doing that, it's going to change where the weld lines will be. What's the output? Again, let's read the flow result. And obviously it's going to fill in a different direction, right? Because the gate location is set differently. So now we see that it's filling from right to left. And when we look at the weld lines, we realize that this is actually a lot better than what it used to be. So in my previous design, if you remember, we had a lot of weld lines in this area. We had a lot of weld lines located over here, many weld lines. Now we only have a few over here. So those could, you could say those are negligible. It's not going to have much effect. It's still much better than my previous design. So this is great. Let's talk about how we can still optimize further this design. One of the things I want to look at now is the pressure at the end of fill. Now I'm looking at that pressure, and we see that pressure listed here, which is about 47 megapascal. A typical injection machine is going to push about 100 megapascal. So you could say that I'm still well within the limits of my machine, but I'm preparing myself to do a family mold. So I don't want to have a mold with one cavity. You have multiple cavities. So I know that by doing that, it's going to increase the pressure required to do the injection. So at this stage, I want to see how I could actually reduce the pressure at the end of fill, and we're going to do that by trying different material. So I like the gate location, I like the model. So now let's try a mix of ABS and polycopolymer as my material rather than just PC. So we know that ABS PC by experience flows easier, doesn't need as much pressure to fill a mold. So let's see how that stacks up using the same gate, same design. And now using this material, we see that now we reduce the injection pressure to 30, 38 or something, where it used to be close to 50. So this is a good design, a good choice to go on and continue our design, or at least figure out which best scenario works in our model. So if we review a little bit the scenario, so we went through actually a number of scenarios quite quickly. So the first scenario, we saw that the part was just too thick. There was some race tracking around the part, a lot of weld lines, cooling time was too high, not a good design. Second one, we got a short shot. So obviously off the gate, short shot, no good. Then we redesigned. We found the happy medium as far as thickness goes, but we had a lot of weld lines. That was an issue. Although we reduced the cooling time, the weld lines were still an issue. We moved the gate location. We got rid of the weld line problem we had earlier. But again, thinking forward that this is going to be into a multi-cavity mold, I wanted to reduce the injection pressure so I could actually use that into a multi-cavity mold, knowing that the fact that having multiple cavities in a mold will increase the pressure. We wanted to do that. So the happy ending was the mix of ABS and PC material with the second gate location, with the optimized model thickness. That's my ideal design. So very quickly, I ran through 5 scenarios, and I did that within maybe 5-10 minutes. So that's the power of what SolidWorks Plastics can do for you. You can actually do those scenarios before you start doing anything else and manufacturing the mold, which can be quite expensive. So we explored the best option, and now we're actually going to dip a little bit into mold making itself, where we want to do a family mold and we want to do runner balancing. So if you're not familiar with runner balancing, I'm going to illustrate what runner balancing is and why it's important in mold design. Before we do that, let's actually jump and look at our family mold layout. So over here, I'm going to go to my family mold. So as you can see, and as it's loading all my plastics results and updating my part here, you'll see that I have a mold, a 4-cavity mold, and I'm basically manufacturing 2 smoke alarm at the same time, top and bottom of each of the parts, right? So we see the top, the bottom, top and bottom there, and now we can run the flow analysis, look at the results. And one thing that is key when we do a family mold like this is to have the fill time to be equal in all the components, and that's not easy. Now, the reason why we want the fill time to be equal, or we want all the parts to fill at the same time, is to make sure that there's material is equal in every sense. The finish is equal, even the physical properties are the same. So now, if I kind of roll back the timeline here, you can see that the covers, the outside covers with the grills over here, we can see that those here, they're already filled up completely, and while these here are partially filled up. Now, again, the reason why we want to have the fill equal in all the components is that so the parts are done at the same time. So time-wise, it's good, but also to have the same finish, the same physical properties of each of the components. And the way we do that is to do a runner balancing. So my runners, which feeds the plastic, the molten plastics to the part, we can size them differently so that it controls the flow. So if I switch to my layout where I've actually done my runner balancing using SolidWorks Plastics, you'll notice that SolidWorks Plastics doing a runner balancing analysis will actually go in and size the runners so that the parts do fill in exactly at the same time, and they fill in equally. So again, as it's loading my results, you see that some of the runners are actually smaller than the others. That's to control the flow inside of my cavities. And when I run my simulation, you'll notice as it's filling that now all the cavities are filling at exactly the same rate. So when the mold is completely filled, it's completely filled for all the parts at the same time. So, and the idea again with runner balancing is to ensure uniform product. If some of the parts fill in before the others, the part might actually look different, feel different, even have some physical properties might be different as well. So what we talked about today. So we covered how just using SolidWorks, some of the design tools inside of SolidWorks can save some time in the design stage, even eliminate some flaws using some of the tools inside of SolidWorks like draft analysis, undercut analysis. And then when we moved to plastics, we saw how it was quick and easy to set up a simulation, just a few steps. Then we quickly understood the challenges that were in my current design, that we needed to do some changes. And when we start doing those changes, I was able to just explore a number of options that before or without SolidWorks Plastics, I would have had actually to manufacture some molds, which can be quite expensive. So I can save that guesswork and do all of the guesswork inside of SolidWorks Plastics and take out the guesswork. We picked up the best option as far as part geometry, as far as gate location, as far as material selected for the part. And then at the end, we started do a little of mold making and see how we could do a runner balancing analysis to make sure that in a family mold or a multiple cavity mold, we have a equal distribution or fill of all my cavities. So if we wrap up using a customer, so Echo, they do a lot of plastic part design and simulation. I mean, this is what they told us. If we didn't have SolidWorks Plastics, we wouldn't have as much confidence in the manufacturability of a design. It helps us avoid going back and forth with the mold maker after the fact, which saves time and reduces costs. And that's really the idea with SolidWorks Plastics. Now, today, I talked about SolidWorks Plastics to introduce a little bit what SolidWorks Plastics is for more for the part designers, maybe a little bit for the mold makers. But we're going to follow up on this presentation next week with my colleague Sashi, who's going to talk about how to use SolidWorks Plastics for mold cooling analysis and warpage prediction. So if you're interested in that, next week, next Friday at 11, Sashi's going to be online, and he's going to talk about some of the more advanced functionality of SolidWorks Plastics, more for the mold makers, mold cooling, and part warpage. So as such, I think this is going to be the wrap up of our session. Both Joel and I are there to answer questions. I didn't see any questions come up during the presentation on plastics itself. But if you have any questions that come up after the fact, please don't hesitate and send us a quick email, and we'll get you the answers you want. So on that, I'll wish everyone a great Friday afternoon, a great weekend shortly coming up, and I hope to see you soon. Thank you.
Thanks, everyone. Bye, Michel.